Okay, I'm not sure if you heard anything from what I said. So thanks, Florian, for your perfect introduction. Yeah, as Florian mentioned, my expertise is deep learning, machine learning, and I'm particularly interested in developing methods for biomarker discovery and to support precision medicine, so tailored therapies for patients. And the idea of today's talk is to give you a little bit of idea on machine learning and deep learning basics, and at the same time connect that with biomarker detection and how kind of this can help patients in the end. So let's start with a short overview of what precision medicine is about at all and what are biomarkers or what is biomarker discovery about. So in a usual setting, we have a patient population with patients, and we have probably images or other data about them. And then we have particular knowledge about patients, and we treat them according to this knowledge. And in a perfect scenario, we have tailored therapies, and patients with different characteristics will be treated with optimized therapies. But of course, this optimization of therapies and this treatment or division of patients or detection of subgroups of patients depends on our knowledge. And this is where biomarkers come in, because biomarkers are somehow defining the characteristics of a disease, so they define our knowledge about disease. And so biomarker discovery extends our knowledge, meaning that with extended knowledge, we can develop new treatments or treat patients in a more optimal way. So this is somehow the life cycle of how all this comes together. In a more specific way, when we look at it in a little bit more specific way, we can use new biomarkers for a more early diagnosis, which can sometimes lead to a much better outcome of the patient. So if you think about a tumor that is detected in a very early stage, then treatment is much easier compared to when we detect a tumor in a quite late stage. Then the early identification of subgroups is sometimes also very important, because if we treat patients with a non-optimized therapy over a longer period, then function may be already lost. And then when we switch to the optimal therapy at a later time point, then we already lost some function or some health of the patient, so to say. And last but not least, tracking the progression of the disease is also something where biomarkers are important, because it allows us to manage the treatment of the patient and to adjust the therapy accordingly throughout the disease. So why is imaging data so nice to look at? So on one hand, it's non-invasive. On the other hand, it's kind of the sweet spot in the middle where it provides a certain level of detail about the patient. And on the other hand, big data is available. So both properties are needed for biomarker discovery. So here we have a short illustration of why big data is important. So if we have just a few data points or a few samples available, we may think, oh, well, this is one cluster, so we can treat all of them in the similar way. But when we collect more data or more detailed data about patients, then we may realize, oh, well, we have subgroups of patients, so we should treat them in a different way. And this allows us then to have this optimal treatment to have precision medicine. So now that with big data, we also need to explore this big data. And here's where machine learning comes into play, or artificial intelligence in general, machine learning offers an explorative way to discover unknown markers. So I've just put here this nice illustration of AI, machine learning, and deep learning, because artificial intelligence, kind of everyone is talking about it, but in the end, it also kind of contains programmed decisions. So it mimics human behavior, but it can also be like if-else decisions that are hard-coded. Machine learning is mimicking human behavior or learning from data, mimicking human behavior by learning from data. So you have input and output, and you learn this relationship. And deep learning is just, so to say, a subset of machine learning, which is quite powerful and comes with a lot of advantages. So how can we train these models? So on one hand, with supervised learning. So when we have input data, we have a specific target. So we need manual labels for that. In the medical domain, usually this is done by doctors. So they are costly. And it's also the question, when we want to detect something new, what should we annotate at all? So supervised learning is just one part of the picture, and unsupervised learning is here a really nice extension, or self-supervised learning, how is it called nowadays quite often, the idea is to circumvent this need for large data sets with a lot of labels, which are costly, and to learn directly just from the images without labels. So here I just provided an overview about all these different strategies that you have. So we have just discussed the supervised setting, where we have a label for each data point. Then we have the unsupervised setting in the third column, where we have no labels at all, and we just try to learn some structure in the data itself. And then we have some things in between, of course. So we have the weakly supervised setting. So you can think of about you, instead of letting medical experts label your data, you can also put them online and just let other people annotate it. And this way, some of the labels may be good, but others may be wrong. So you will have some kind of weak labels in this case. And in the semi-supervised setting, you also try to combine the best of both worlds. So you make use of large unlabeled data sets, learn some structure in them, and then in a second stage, you fine-tune them on small labeled data sets. So to be more concrete in today's talk, we have, I kind of just put here the use case for us, so we can kind of always refer to some practical projects and practical experience that we have in developing the models, and how this kind of really works in research and in real world. So today I will focus on optical coherence tomography imaging, which is a non-invasive imaging modality in ophthalmology. It's widely used. So actually in our clinic, each patient that comes at each visit will get a OCT scan. So this is done in a few seconds and provides you with this three-dimensional volume of the human retina, which you can see in this video on the right-hand side. And if we look at this cross-sectional scan, you have really detailed information on the cellular level. So it provides you with a lot of data that you need to explore, and where machine learning is needed, because manually this is practically not doable if you think that one image volume contains like 65 million pixels, depending, of course, on the acquisition protocol. But yeah, so the problem setting that we have here, the concrete, is that we know some markers, but these known markers are not enough for the diseases, which are quite common and affecting the vision of patients. So what we need are tools to explore the rest of the images, to explore the rest of the markers that we do not know about yet. So here is an overview of how we can perform this biomarker discovery. So 5 different strategies we came up with, and we'll go through them one by one. We will now refer to kind of basic concepts, and then link them to how they're extended and applied in practice to discover biomarkers. So the first approach is to use traditional supervised prediction. So we first define features of interest. So this can be anything in the image: brightness, thickness of the retina, tumor size. Then we train a traditional machine learning model on that, and then we evaluate the value of these handcrafted features, or these handcrafted markers, in a prediction task. So in general, in machine learning, to solve a task, we need different parts. So we have a learning task, and we have in this learning task that we want to solve, we have a model that we train, which is on the right right-hand side at the bottom. We have data the model is trained on. We have an objective function that defines, that gives the model feedback on how good it's performing during trainings, and then can optimize its parameters. And then we have the optimization algorithm that kind of takes the error from the objective function and optimizes the models. These are the different building blocks in machine learning in general. And how we combine all these things together define our training paradigm, or define then in the end our model or our approach. So as I said, the typical pipeline, or the traditional pipeline, which was used before deep learning, is using handcrafted features, and on top of these features apply a machine learning model. So here you can see this pipeline. You have the input, then you have a human hard coding the features, and then you train a machine learning model on top of these features, and then you have the output. Or you can train the model to get a specific output. Examples for these handcrafted features, I just mentioned them. So here's just a visual example for what I said in words. Is the thickness of the retina is one feature that is often used in ophthalmology to describe the disease path and also the status of patients, which is of course a quite rude measure or quite coarse measure, but yeah, it's one of the widely used ones. So now I also kind of try to do some buzzwording, so which is I know maybe not so satisfactory for you, but I try to kind of mention all the important stuff and then just pick out some of these words and explain them in more detail. So here there are multiple traditional supervised approaches like linear regression, logistic regression, decision trees, support vector machines, neural networks in its classical form, so not in a deep form, but in a shallow form, nearest neighbor. So these are all things you can try out if you have not enough data, because this is the setting where traditional machine learning is still useful. Yeah, but I will focus now just on a few of these models. So in linear regression, you have a continuous target. So for example, one input feature could be the lesion volume or the retinal thickness, and then the prediction target is the survival time of a patient. And then you try to fit a line that describes this correlation or this relation between the input feature and the output in the best possible way. This is of course a very simplistic model, but it's one standard model that you can apply to get some prediction out of simple features. Another technique is support vector machines. There you solve a classification problem, and the idea is that in your feature space, you try to optimize two classes that you have by a hyperplane. There are different kind of different techniques how you can create this feature space within the support vector machine. In its simplest form, it works directly on the defined features, and yeah, as I said, it just tries to define the hyperplane that separates the two classes in the best possible way. And the classic neural networks, I also wanted to mention them because they exist since decades, but they were used in a different way as nowadays. So they were always fully connected, they were shallow, and therefore not as powerful as today's deep neural networks. And last but not least, the random forests. This is now the method that we used in one of the projects I will present to you, is an ensemble of decision trees. So these decision trees are constructed in a way that you select at each node a feature, for example, the lesion volume, and then depending on the lesion volume, if it's bigger or below a certain threshold, you go left or right in the decision tree, and you do this construction of feature selection and threshold definition at each node, and in the end, you get a decision tree which you can just traverse for a new sample according to its features. And once you reach a leaf node, you will get a decision. And you construct a lot of decision trees which form then your random forests. And the basic idea is that for each decision tree that you construct, you take a random subset of your training data set, you take a random subset of the features, and in this way, each of these nodes will have a different view of your data, and your models will be more generalizable to new unseen data. So as I said before, you can use these models or this strategy of handcrafted feature definition and traditional machine learning models to discover biomarkers in the data. So in this case, the task was to identify those patients that need a lot of treatment. So to identify the high risk group. In ophthalmology, you always have this initiation phase where all patients get treated in the same way. So they all get monthly injections until month 3. And after that, the treatment is more or less undefined or unclear. So we defined features that we knew that, or kind of where the doctors thought that they would be relevant for this prediction task. So we took volumes of lesions that we segmented. We took the thickness of the retina and other features. And then we fed a random forest model with that to differentiate between high risk and low risk patients. And where now kind of this biomarker discovery process comes into play is these random forests allow to compute feature importances. So for each of the features that we used for training the random forest models, we could calculate an importance score, and in this way we got a ranking for the features. And in this case, we identified that a specific fluid volume, a specific fluid in the central part of the retina was actually a protective factor for the disease progression. And before we kind of identified that, patients were actually treated when they had this fluid because doctors did not differentiate between different types of fluids. So it really had an impact on how patients are treated nowadays. The second strategy is to let a supervised deep learning model to train a supervised deep learning model to segment certain structures of interest in the training data. And then once you have this trained model that is able to detect specific pathologies in the data set, you can apply them on a large scale data set, which is sometimes or quite often actually collected in routine imaging, but cannot be used directly. But with kind of these models, you then can explore these large data sets and evaluate them in post-hoc medical analysis. So what is the difference between machine learning and deep learning? So burned down to the most basic thing, it's you get rid of this feature extraction part. Instead, deep learning networks are able to learn directly from the input the relevant features for a specific task, and this is why they are also so powerful, because as long as you have enough labels and enough data, which is also kind of illustrated in this graph here on the right-hand side, you usually always outperform the traditional machine learning approaches. So what is now the difference to these classical neural networks that are introduced before? The basic difference is that instead of this shallow structure, you have a lot of layers, and each of these layers adds just a little amount of complexity to the whole network. But in total, the learned representation is quite powerful. So in this example, you can think of, you have the faces input. In the first layer, you detect the edges. In the second layer, you combine these edges to eyes, to noses, to the mouth. And then in the subsequent layer, you then again combine these features into face types. And then in the last layer, you're able to detect a specific face. What I wanted to illustrate here is exactly what I kind of just showed in this very simple illustrative use case, is that when we look at kind of the whole development of deep neural networks, they're getting larger and deeper, and kind of this depth really adds the power to these networks. So there are some aspects that enable the training of such deep networks. So unfortunately, the time is not enough to go into all the details. But if you're interested, you can, of course, reach out for me, send me an email, and I will happily to kind of pinpoint you to some tutorials or to some relevant papers. Yeah, so these are the networks, sorry, what I forgot to mention here is that these are all networks which are dedicated towards classification or regression. So you have the input image, and then you have, for example, the output deceased, non-deceased. But the task we were looking here is the segmentation task. So you have an input image, and for each of these, sorry, the slides are in the wrong order, but this should be the next one. So for each input pixel, we try to predict the class of this specific pixel. So in this example, we have the input OCT image, then we have the neural network in between, the segmentation network, and then we predict background, which is black, red would be the retina, and then green and blue are some lesions within the retina. And some popular, kind of the most important architecture actually that is used nowadays for segmentation in the medical domain is the UNet. Researchers are already sick of these words, I guess, I guess. But yeah, it's still more, from my perspective, the first thing you should try if you have a segmentation task is the UNet. So the principle, the basic idea is that you have, on one hand, this encoder on the left-hand side. I'm not sure if you can see my mouse, but you have the encoder here. So you learn features with convolutional layers, which are dedicated with the indicated with the blue arrows. And then you reduce the spatial size with max pooling layers, which are denoted with red arrows, and so on. And you do this one after another and again until you reach the bottleneck layer. And there you have kind of this very abstract representation, I would say, but which is not very localized, of course. So you need a decoder to reconstruct the original size of the input image, because you want to have a segmentation map where each pixel gets a class. So you reconstruct the original size of the image, and this is done in the decoder. And therefore you combine this abstract, non-localized representation with localized information from the decoder then. And yeah, you can find all the architectures that are just listed here. Should be available in TensorFlow and PyTorch. So these are all things that you probably already tried out yourself. So as I said before, so training these segmentation models is also kind of a way of discovering biomarkers. So you segment these markers, and then afterwards you apply it to a large data set, and you can do then more sound medical analysis with this tool, with the segmentation model. Another strategy of detecting biomarkers is to first define a prediction target of interest. So this could be a specific disease class or visual function, or, as we had before, treatment need, where you also are not sure which features of the image or which structures in the image are important for this particular task. But instead of handcrafting these features or defining a segmentation model to segment and analyze this then in a very costly way, is you could just let a classification or regression network learn this relation, which is here depicted in stage 2, so training with labeled data. And then in the third step, you then analyze this learned model. So here, techniques for interpretability of these models are important. So on one hand, it's nice because you do not need these pixel-wise manual annotations where you have to train your segmentation model on. But on the other hand, these interpretability techniques are whole research area itself, but still it can provide some insights on how the models work. So usually what they try to achieve is you have an input image, you have a certain output of the network, and then what these techniques provide you with is a map of importance. So which part of the input image, which parts of the input image were important for receiving this exact prediction. So in the clinical setting, or in our use case scenario again, you can train a model on disease classification. So AMD, PCV, and RAP are different types of diseases. And you can train a model to classify between these diseases and then use these interpretability techniques to visualize the areas of importance. And here in this example, we can see that the central part of the retina was the most important area for discriminating between those diseases. This is just an example which is not very exciting, to be honest, because this was already known before, but it kind of illustrates the idea of analyzing a model and then deriving some conclusions from it with these techniques. A library which I can highly recommend for these interpretability models is Captome. So this collects a lot of these interpretability techniques, and makes it much easier for users, for end users, to just apply them to your network, and then you can visualize the important areas. So the fourth possibility on how to discover biomarkers is unsupervised feature learning. I think these last two things are particularly interesting because they're have a more exploratory nature. So in this unsupervised feature learning approach, you train with unlabeled data. So the advantage is, of course, that you're not biased towards a specific task. You also do not need labels. On the other hand, of course, it's much harder because to find a good representation or to find good features without having a specific target is a very hard task. But the idea is quite similar to what we have seen before. Is first step, train a model and then analyze the results. In this case, you learn features from your data, and then you analyze the features instead of the model. So here again, some buzzwording from my side. So very popular approaches nowadays, or well-known approaches, are autoencoders for unsupervised learning, generative adversarial networks, or contrastive learning. I think the last technique, namely contrastive learning, is a very interesting approach and very powerful. I will describe autoencoders because we use them in one of our techniques. So we have the direct relation again between the basics and the use case. So in the idea of autoencoders is quite simple. So you have an input image, and then you have again this encoder-decoder structure, but instead of instead of getting a segmentation as output, you encode the input image into a compressed representation, so into a few features. And the idea is that the encoder needs to throw away all the irrelevant information and just learns a representation that describes the data in a good way. And then with the decoder, you try to reconstruct the input image. And only if the features are good, you're able to reconstruct the input image. I mean, this is just one example of how you can do unsupervised learning, but it's one of the most widely used and also one of the most successful approaches in unsupervised learning. In our OCT domain, again, we train the unsupervised autoencoder model to learn features on different levels. So we called it local and global level. So in the first stage, we learned a representation using autoencoders for each column of these volumes, so called A scans, meaning that we got a representation of a specific position of the retina. And this is this what we call local feature embedding, or the local features. And then afterwards, so meaning that we have now this 3D volume, and in this A-scan dimension, we reduce the number of dimensions to 20. And afterwards, we used another autoencoder trained on this compressed feature representation to learn so-called global features that do not encode the retina at a specific position, but the condition of the retina as a whole. And we, after training the model, we did an evaluation together with physicians. And what was really nice, so we learned on one hand features that were known before but have not been used. So that was quite nice, because that was kind of a potential knowledge discovery, so to say. Then we discovered features that were known before and have been used, so which justifies that the feature representation that we learned is really useful. And last but not least, we also discovered features that had no correspondence to known features. So we argued that these features corresponded to some vessel structure below the retina or in the deeper part of the retina, but this is something that we still have to investigate. And regarding the global features, we evaluated their value so we evaluated the value in terms of how good they are in prediction function, because this is always a desirable target, because the available visual function measures have all they are all quite limited and are quite noisy. And what we've seen that compared to traditional markers that have been used before, we could improve the performance by a large margin. Yeah, so the fifth and last part of doing anomaly detection, of doing biomarker discovery, is using anomaly detection. So the idea of anomaly detection is to detect the appearance out of the ordinary as candidates for markers. So if you think about this unsupervised learning strategy, you just try to learn a representation of the whole thing, of the whole data set, but this by definition will probably also encode some noise. It may encode healthy things that you have in the retina, which you're not particularly interested when you're looking for biomarkers. So because diseases alter the morphological appearance, so a natural way to look at to look for these markers is to just focus on the anomalous parts. So if you think of, you want to detect these anomalous markers or these biomarkers which have an anomalous appearance in the whole data set, in the whole feature space, it's like, first, I always compare it with searching for a needle in a haystack. But if you first perform anomaly detection, so meaning you separate the healthy or the normal part of your morphology from the diseased part, you're able then to concentrate on these anomalous parts, and the task is much easier. And then you can, we call it generate the vocabulary of visual markers, but yeah, this is just a different wording for the same thing. I will present now two approaches how we perform the anomaly detection in OCT images. So this is the first one, where we used a specific type of autoencoder for learning a feature representation on healthy OCT patches. So in the end, we got a feature representation of only healthy data. And then we trained a so-called one-class SVM. So if you remember the support vector machine, the SVM that I've introduced several slides before, we had this hyperplane that separated healthy from diseased cases. And the one-class SVM is a specific variant of this support vector machine, where instead of a hyperplane that separates data, you try to find a sphere that best describes your healthy data that you have available, and everything outside of this sphere will be, so after training, after you have defined your sphere, will be detected as anomalous. So this is what you see here then in the bottom row. After you have trained your one-class SVM with the hypersphere, you put in the unseen OCT, and for each patch, so at each position we extract a patch. We apply the autoencoder to get the feature representation. Then we apply the one-class SVM to define if this feature or if this patch is lying inside the hyperplane, which would be then identified as normal, or if it's lying outside, which would be then identified as anomaly. And separates the retina into normal and anomalous regions. So you can see here some examples with original OCT scans, manual annotations, and predictions in the last row. What we've seen is that it somehow really is able to identify the anomalous regions, but there's still room for improvement, which is why we developed the second method that I will present to you afterwards. But besides this potential improvement potential in this method, what we did here is what I said to you, we identified the categories. So the first part was exactly what I said before. So anomaly detection, we separated the normal from the anomalous cases. And now in the second step, we focused on these anomalous areas and tried to find markers in there. So we performed clustering of these patches, and I think the most important thing, because I think we're running out of time, is if you look at the right-hand side, if you look at the identified clusters in the early stage of the disease and the late stage of the disease, which is early and late AMD, denoted here in the slide, you can see that we identified the same clusters in both diseases, in both disease stages, but additionally, we identified in late AMD a cluster that corresponded to fluid, which is exactly reflecting the disease progression course, because in early AMD you do not have fluid, and in late AMD you have. So we could prove that both the embedding and also this clustering and identification of markers or potential markers made sense. And then we, as a last project I will present to you today, as I mentioned before, was the improvement of this anomaly detection approach. And the basic idea is to use anatomical knowledge about the structure you're interested into to improve anomaly detection. So there are different types of uncertainty prediction that we have in data. So there was some paper from 2015 by Gall et al., which defined some different types of uncertainties and techniques how to derive them. So one uncertainty is the aleatoric uncertainty. So this is the uncertainty of the task or data. This is uncertainty which you cannot change. So this is, you can see here in this example, this uncertainty is high in areas where the resolution is not good enough to differentiate between the different objects, for example, and so on. But the epistemic uncertainty is the uncertainty that we are interested into because it defines the uncertainty of the model. So if you have if you have a new image, in this case here, this street view image, and you have a pavement which you have never seen before in your training data, so the model has not seen it before, it will give you a high uncertainty in this area. And this is what we want to make use of, or we made use of in this data. So we combine it with an observation that which is called DRILL, so disorganization of inner retinal layers, where we realized that, or which is actually known, but we discovered it for our problem to be very useful, is that if you have a healthy retina, these layers are nicely distinguishable, but once the retina gets more diseased, the layers get disorganized and are not distinguishable anymore. So what we did is we trained a segmentation network on only healthy scans. We also did not use manual labels to train this model because there are already models available that work, traditional models available that work nicely in a well-defined healthy environment. So we just took weak labels to train our model on normal B scans. And then during application time for anomaly detection, which is the second step here, is we apply this model for layer segmentation, but we're not interested into the layer segmentation, but we're interested into an uncertainty map of this layer segmentation. So the theory was that we get uncertainty in those areas where we have this disorganization of layers. We have high uncertainty in those areas which have not been seen during training, meaning that uncertainty should be high in anomalous regions. And this is exactly what we have seen, also what we have observed in our results. And actually the results were, we were astonished how good this worked. So you can see here manual annotation and manual annotations and the output of our model. And actually in some cases, I'm not really sure which one is better. So what is also nice is that these anomaly detection techniques also naturally extend to other diseases, because the training is just done on healthy scans. So it detects anything that is deviating from this normal appearance. So you can use that for all kinds of diseases. So in conclusion, what else shall I say? If I'm working in this domain, I have to justify somehow what I'm doing. So machine learning and deep learning is powerful for exploring image data. And there are multiple strategies available. And I think the hard task here is, on one hand, to identify the strategy that most suits your needs, and also then to optimize and develop it in a way so it's really useful for your specific problem. So some things you have to consider when you want to do this is, do you have a clinical hypothesis? Do you have a specific question or aim that you're looking for? How many patients and images do you have? Which modalities are you working on? This may also define the models that you have to use, and which type of labels do you have available. Do you have pixel level labels available already? Then you could train segmentation models. Do you have only image level labels? Then you could train classification models and analyze them. Or do you have no labels at all? Then probably anomaly detection or unsupervised learning are the way to go. I'll try to summarize that. I'm not sure if these slides will be made available, Florian, afterwards, but I just summarized kind of these take-home messages here, so you can have a look at it afterwards. So I'm not sure if you want to go through that, or if we have time to go through them, but otherwise you can have a look at it afterwards. Florian, do we have still 1 or 2 minutes to go through them, or?
I think we're going to close here for the sake of time. And thank you very much for this really interesting presentation. And I don't know, you can see me now.